Good evening, everyone. I would like to welcome you specially again to this week edition of CHM204. By God's grace, today we are going to be looking at the topic 6, where we're going to be looking at the second period and higher main group elements. Specifically, we shall be looking at group 13 and group 14 elements, their behavior, their chemical reaction, their uh, importance, and some other very important things about them. So my name is Tiola Inka Jani, your facilitator for this class. Thank you and stay tuned and stay blessed. Today we are going to the unit 2 of the module 3, as I've earlier said, where we are going to be looking at the second and higher main group elements. But this series in module 3 will be looking at from group 13 to group 18. But for this week, by God's grace, the unit 2, we shall be zooming in on the group 13 and group 14. So at the end of this topic, the learner should be able to, number one, know and classify the elements included in group 13 and 14, understand the electronic configuration of group 13 and 14 elements. We must know the concept of inner pair effects. We must know the reaction involving group 13 and group 14 elements. And must also be able to know the application of some of the elements in group 13 and 14. Introduction to the higher main chemistry. When we are talking about this, we are talking about main group elements, which are the S and the P block elements. And we have looked at the alkali metal, which are the group 1. Today we are going to be looking at the group 13, which is otherwise known as the boron family, and group 14, which is also known as the carbon family. The second period elements of each group differ from that of the heavier member. What we are trying to say is that the period 2 in the main group elements is highly unique, because the elements there are always the number 1 in the list of the group. They will have a very small size compared to other elements under them in the same group. And therefore, because of this, they will have some behavioral pattern that is unique for them alone. Like, for example, when you look at the group 1 elements, the first member of that element is lithium, which is in period 2 of that group 1. Under him is now the sodium, the potassium, downward like that. But this lithium have a completely different behavior because of that its unique position. So the element of period 2 are very important to look at them specifically, ranging from group 1 to 2 and from group 13 to 17. And the elements that are in this period 2 across the main group elements will be in group 1, you will find lithium. In group 2, the second period element in group 2 is beryllium. In group 13, remember there is a blockchain of 10 elements, which are the P block elements, before you come to the next group. That's why that next after 2 is 13. Instead of group 3, we used to call it in the olden days. It's now group 13. In order to make sure that the 10 elements of the transition series are captured in between group 2 and the next group. So the group 13 is the boron family, and it is so named because the first element in that group fall in the second period and has its unique behavior. The group 14 is the carbon family. The group 15 is the nitrogen family. The group 16 is the oxygen family, and the group 17 is the fluorine family. But instead of calling it fluorine family, you can otherwise call it halogens. And when we look at it, we are saying when the principal quantum number is 2, you will find this series of elements in period 2 of each of their group. Lithium is in period 2 of group 1, beryllium is in period 2 of group 2. And they differ from other heavier members under them in so many unique ways. So when we are looking at boron family, for example, underneath boron in that same group 13, the second period is boron in group 13. Underneath him in group 13, the third period is aluminum. The fourth period is gallium. The fifth period is indium. And the sixth period is thallium. But the first member is the boron. It will differ from the heavier member of that same group, which are the aluminum, the gallium, the indium, and the thallium. So element of the third period. The third period is when the principal quantum number is equals to 3, which means the electrons are filled into 3 shells. You remember, if you go through group 1, the period 2, you will be finding lithium in group 1. In period 3 of group 1, you'll be finding sodium, because sodium has 11 electrons, which is filled into 3 shells. That's why we say N is equals to 3. So all those elements in period 3, they are heavier than those one in the period 2. So the element in period 3, for example, will now be sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. And what we are trying to say there is that fluorine is up there as the first element of halogen family. Chlorine is heavier than fluorine. Fluorine will have a specific behavior different from what fluorine has. So generally, the elements of the third period are generally more representative of their group more than the one on top of them, which is in period 2. Because those one in period 2 have some behavior that is making them to be different from the general trend of other members of their group underneath them. But the next period under them, which is period 3, has a lot of similarity with other ones that are in period 4 and 5. And that's why we say the period 3 actually represents more representative of the group than the period 2. Anomalous of chemistry of second period elements result from 3 very important characteristics. The first one is that they have very small radius. Radius for one element, radii for more than one element. The atomic radius is small because the number of shells through where they fill in their electron are not more than 2. And you remember, as the shell is increasing, the radius of the atom will be becoming bigger and bigger. So the second period of all the groups have that abnormal behavior or abnormality in their chemistry because of 3 things. 1, their peculiar small radius. They have very small size. 2, they have the possession of energetically unavailable d orbital. Because when you talk about the second period, N is equals to 2 according to principal quantum number. And at that time, the only orbital that is having enough energy to sustain and to retain electron will be S and P orbital. So in the second period, there is no availability of energetically present d orbital. Before you can be talking about the d orbital or filling electron into the d orbital, you'll be talking to you'll be going to the third period, which is when N is equals to 3. So because of that second period now, there is no availability of the d orbital that could be making use of. Then the energy, the electron transfer or the electron location cannot be in the d orbital. And that's why they cannot expand their octet, because the d orbital have 5-fold degenerate that can make it to have maximum of 10 electrons. But those elements in period 2 cannot do that because of their small size. And that's the reason why they have some anomalies. But by the time you are coming to period 3 to period 4, they have d orbital that is highly energetic, that have the tendency to receive electron when you are transferring from the ground state to the excited state. And the third reason is the tendency of this second period element to form pi bond with other atoms. You remember that in the second period, we have the s and the p orbital, and this p orbital is threefold degenerate: px and py and pz. The unhybridized p from one atom can have a lateral overlap on the unhybridized p from another atom, thereby leading to the formation of additional bond, which is pi bond. So they have opportunity to form two atom bonded with a double bond. And that double bond is made up of sigma bond and the pi bond. These are what brings the uniqueness to them. Like, for example, when you look at the group, if you look at the group 5 elements, there's the element in the second period there is nitrogen. Nitrogen exists as a divalent diatomic molecule. Nitrogen exists as N2. Oxygen exists as N2, as O2. These are because of the presence of a sigma and a pi bond, and that pi bond is as a result of overlap from the p orbital of the two oxygen atom. So we are going to be looking at each of these three parameters one by one. Effect of small radius on the second period. Small radius is actually responsible for why the elements in the second period have electron affinities that are less negative than normal. Their electron affinity is less negative than the normal. You know, electron affinity is talking about the love of something to attract electron to itself. And therefore, other period under them, 3, 4, 5, they have the capacity to have a higher, strong electron affinity. When an electron is added to such a small atom, that means the atom of element in second period, what happens is that it leads to the increase of electron-electron repulsion. You remember that when their size is very small, those electrons that are in that orbital will be so close, will be feeling the effect of each other strongly. An electron is negatively charged. When that happens, there will be a repulsion, and as they are repelling each other, is destabilizing the anion that is supposed to be formed. And this is the reason why elements in this period to have this issue concerning that the atomic radius is small. But if the atomic radius is big, then the distance from one electron to another will be far apart in such a way that they are not feeling the too much repulsion because of their negative charge. Also, the small size of these elements in second period prevent them from forming compound in which they have more than 4 nearest neighbor. What we are trying to say is that these elements in the second period, they cannot extend beyond octet configuration. They seek and tend to obey the octet rule. Anything below that is okay, but anything above that, they cannot form. So the 4 bond can come around them towards that center, and each bond is made up of 2 electrons. So it will have formed 8 electron system, and that is it. But for them to have opportunity of getting 10 electron system, they will not be able to, because they don't have the d orbital that have the capacity to accept electron above the 8. But when you are talking about the electron acceptance within the 8, it is possible for the second period alone. Why? Because second period is made up of the s and the p orbital. And you know s orbital will take maximum of 2 electrons. P orbital will take maximum of 6 electrons, with 2 in px, 2 in py, and 2 in pz. So they take and tends to form an octet chain. So if you have an atom, let's say you have an atom A, if it is in second period, it cannot have more than this kind of bond. And each of these bonds is made up of 2 electrons. So that's what gives the total of 8 electrons. So if you look at boron, boron cannot take more than 4. In fact, in most cases, which is one nature, it will take 3, BF3, which makes it to be incomplete octet, because this will be 2 electron, 2 electron, 2 electron, making 6 electrons. They can have less than 8, they can have up to 8, but they cannot have more than 8. But immediately you are coming to the third period of group 3. Under boron, you will be having aluminum. And when you come to aluminum, you have a tendency that you are in the period 3, which means that d orbital is available. And you know d orbital have 5-fold degenerates, so it has more space to accommodate an electron pair each into each of its suborbital, and therefore making it to have up to 10 bonds or more. If you look at the group 5, nitrogen will not exceed that 3 or 4. That's why in ammonia you have NH3 as a sp3 hybridized system. Na3 is made up of 6 electron pair, and there is a lone pair of electron he has not used, which makes it 8. But he cannot have more than this and still retain neutrality at nitrogen. But if you come to underneath nitrogen, the third period under nitrogen, what you have there is phosphorus. At that place, N is equals to 3. It is in the third shell. So the phosphorus has tendency to have d orbital receiving electron. So in the phosphorus now, you can have opportunity of using S, P, and D. So when S and P has formed it, if there is any extra electron, the D can take it, so we can expand more than that. So if you're looking at, for example, phosphorus pentachloride, you discover that, oh, phosphorus truly is in group 5 like nitrogen, but here phosphorus is bonding with 5 chlorine, and each of the bond is 2 electrons. Therefore, around the center of phosphorus, you are having 10 electron system. The only thing that makes that happen because phosphorus in group 5 is in period 3. But the nitrogen in group 5 is in period 2. You cannot have electron filled into d orbital because there is no energetically favored d orbital. These are the peculiar reasons why you have that. So when you are looking, for example, at BF3, it doesn't have more than that 6 electron, which is 3 electron pair between the boron and the 3 fluorine. So for example, BF3 forms only the 4 coordination or form the 4 coordinates. And the tetrahedral nature of it, which is the anionic BF4, is as a result of now the electron-rich nature, which he has. So, but it cannot form a coordination that is above 4. Whereas under that same boron is in that same group 13 is aluminum, but aluminum under him is now in period 3, not in period 2, which has opportunity to have MTD low line d orbital where it can use to accommodate more or expand more. That's why it was able to form a octahedral field, which is a field that is made up of 6 pairs of electrons around the aluminum center. But boron can never form BF6, despite the fact that boron is in group 13, aluminum is in group 13. So aluminum will form complex with ligands more in an octahedral field, while boron cannot exceed trigonal planar molecular geometry. So the effect of the energetically unavailable d orbital on the period, second period, it is significant to state that the d orbital are never occupied for principal quantum number that is less than 3. You know what we are trying to say here is that, let's just refresh ourselves on the quantum number briefly. The principal quantum number is n. The azimuthal quantum number is L. N is the one that tells you the energy in which the orbitals are. If you have 1s orbital, 2s orbital, for 1s orbital, n is equals to 1. For 2s orbital, n is equals to 2. So 2s orbital is of higher energy than 1s orbital. But we are saying that when you know n is when you can know L. N will be a full number from 1, continue like that, because that 1 means 1 shell, 2 means 2 shells, 3 means 3 shells. But we are saying L is derived from n by saying L will get an integer value from n minus 1 up to blah, 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 0 as a positive digit. So if n is equal to 2, we are in the second period. then it means the L you can have for that will be 2 minus 1 is the beginning. You remember n minus 1. L will never get to n value. Wherever n is, L will start in an atom short or a figure or value short. So if n is equals to 2, as we have in period 2, our L will be 1 up to 0, 1 and 0. And L is what makes us to know the nature of the orbital. When L is equals to 0, we have S orbital. When L is equal to 1, we have P orbital. When L is equal to 2, we have D orbital. So you can see when you are in the second shell, it is impossible for you to have D orbital. Before you can have D orbital, you must have come to the third shell. That's why we are saying it is significant to state that the D orbital are never occupied for n value less than 3, either 2 or 1, because there's no way a D orbital can even come alive as energetically stable orbital to receive electron when n is less than 2, when n is less than 3. But it's only when n becomes 3, which is the third period, that you can now have possibility of an d orbital. What do we mean by that? When n is equals to 3, let's look at what we are saying. When n is equals to 3, then our L will be 3 minus 1 will be the first thing. That is 2. 1, you will be decreasing in 1 unit until you get to 0 and you stop. So when you are in the third period, there are tendency of 3 orbital. You can have S orbital, 1 P orbital, 2 D orbital. This is why we are saying for you to have a energetically available D orbital, you must have come to the third period. So when we are looking at the second period, we discover that there can never be energetically available D orbital for them. And because of this, they cannot expand their object. So these are part of the abnormal behavior that makes them to be different in their behavioral pattern to other heavier members of that same group. The valence electron of the second period element occupies the S and the P orbit, as we have said. The maximum you can have is 2s to 2p6. Anything after that, you are going to the third shell, which is 3s to 3p6, 3d something. But we are now at the second period, they have no more than 2 orbitals that can be occupied. They have the s orbital and they have the p orbital. And that's why group 1 and 2 are called the s block elements, because their valence electron will always end in the s orbital. While group 13 to group 18 are called the p block elements, because their valence electron will always end in the p orbital. So the third thing there is that the d orbital, the d orbital as far exceeds the energy of the 2s and the 2p orbital. So it is not possible to use the d orbital for bonding when you come to the second period. The role of d orbital in main group compound with coordination number of 5 or greater than the coordination number of 5 is somewhat controversial. And lastly, we know that when you are coming to the second period, you can know that it predicts that the coordination number greater than 4 can never be possible, or is quite unusual for second period. Because when we are talking about second period, they have the possibility of having 8 electrons in the atom shell, which is made up of 4 electron pairs. And each of these pair of electrons is standing for a coordination number. So if it's going to have coordination number of 5, where would the fifth one come from? When the highest number of electrons that the s orbital and the p orbital of period 2 can take will be 2 plus 6, which is 8. So that's why we are saying it is impossible for us to have the energetically available d orbital for the second period of every group, which makes their chemistry to be different from the other heavier member of that group. Remember, the last point is the third point here is the tendency to form p orbital. We want to look at that. So what we have been explaining is just this point 1 and 2, which is what makes the second period element to differ from other heavier member. And we are trying to put a full explanation to each of those points. The third is the tendency for them to form pi bond. There's tendency that the second period element to form the species that contain multiple bonds, like nitrogen gas N2, that will be N double bond N. And that N double bond is made up of 1 sigma and 1 pi. What could have made pi bond to come there? Because in the main group element here, where you are still dealing with that, they are supposed to have been a pi bond formation. Because you are dealing with S and the p orbital, they are supposed to have first of all been an hybridization that will lead to a sigma bond by the orbital of those two atoms coming to overlap on each other to form a molecular or hybrid orbital, which is of equivalent energy. But when that happens, we now remember that there are p orbitals there. So if the real hybridization has happened between the S and p orbital, then that collaboration makes them to have a link of sigma bond, which is a strong bond. So the nitrogen and the first and the second nitrogen will now feel the effect of their unhybridized p orbital. So they can have a secondary overlap through their unhybridized p orbital, and that results into a pi bond. That's why they are stable with the bond order of 2, having them to be the atomic molecule, and also having double bond, which is made up of pi and sigma bond. That is the uniqueness of that second period element. All of them, they tend to form gases that are diatomic in nature. If you look at the group 7, you're fluorine. You look at the group 6, oxygen gas. However, when you look at the group 5 here, you discover that the first element in group 5, which is in the second period of that group 5, is nitrogen. And nitrogen will exist as N2 gas. But when you come under him in period 3 of that group 5, what you find under him directly is phosphorus. Phosphorus cannot exist as P2. Rather, the phosphorus can exist as a tetravalent phosphorus, which are 4 phosphorus bonded together by a sigma bond. So what makes the nitrogen to have had a sigma and a pi bond to be stable and more comfortable to be a diatomic molecule and a gas, but the phosphorus that is in the same group with him as in group 15, but because it's in the top period, you cannot form a double bond at that level unless after he has expanded his object to the d orbital. This difference in behavior reflects that within the same group, relative energies of the pi bond and sigma bond differs. Compounds that contain carbon single bond and carbon double bond, there are tendencies there that in that group 4, you know the group 14, sorry, in the new grouping naming is group 14. Group 14 is the carbon family. And the first element of that group is in period 2 of that group 14 and is carbon. But the heavier member under carbon is silicon. So when we look at carbon, carbon can catenate, carbon can form a bond with another carbon. If we can form double bond with another carbon, it can form triple bond with another carbon. It can elongate chain to form bond with 1,000 of itself. That's why you have biomolecules like carbohydrate, like protein, because they have long length chain of carbon catenation. But when you come to that, it's convenient for carbon to form unsaturated bond. A double bonded carbon-carbon is 1 sigma and 1 pi. It can even form a triple bonded carbon-carbon, which is alkyne, 1 sigma and 2 pi. But when you come to the heavier member underneath him, in the same group 14 with him, but in the third period, you will see silicon there. Silicon can only form sigma bond with another silicon. That one will be energetically more favored, but silicon double bond cannot be energetically favored. Another important trend to note in the main group chemistry is diagonal effects, or what we call diagonal relationship. And what is this diagonal relationship? These elements that are in the second period will relate and behave like their next door neighbor in the third period. Let me explain myself. That thing is called diagonal relationship or diagonal effect. If you look at, for example, group 13, we have boron as the second period. Underneath him, we have aluminum as the third period. Underneath aluminum, we have gallium as the fourth period. But all of them in group 13. They are all in group 13. The first member is boron, which is in second period. Looking at group 14, the element in the second period of group 14 will be carbon. The element in the third period of group 14 will be silicon. The element in the fourth period of group 14 is germanium. Germanium. When you come to group 15, the first element there, which is in second period, is nitrogen. In that same group 15, the heavier member of it in the third period is phosphorus. What we are saying about diagonal relationship is that the boron, which is in the second period, his next door neighbor should have been carbon. But underneath that carbon in that next door neighbor is silicon. So diagonally, boron and silicon, we have some unique similarity. Carbon and phosphorus, we have some unique characteristics. And where we are looking at the third period, let's look at the group 2 so that you can see it at least with 3 examples. Group 2, the period 2 of group 2, the first element we have there is beryllium. Group 2, the period 3 of it, what you will have there is magnesium. Group 2, period 4 of it, what you have there is calcium. When you look at this now, this first element in group 2, which is in the second period, is beryllium. It will have a diagonal relationship with the lower member of its direct neighbor. Its direct neighbor should have been boron. The next lower member to that is aluminum. So there's a diagonal relationship between the same thing will happen for group 1. The group 1, the first element in the second period will be lithium. In the third period, you have sodium. In the fourth period, you have potassium. When you look at that, this element for group 1 is this in the second period. Diagonal relationship says this next door neighbor should have been beryllium, but underneath beryllium is the magnesium. You will have a diagonal relationship with magnesium. So we are saying lithium behaves peculiarly in a diagonal relationship manner with magnesium. You can see that here. The beryllium in group 2, we have a diagonal relationship with aluminum in group 3. The carbon, we have that, and that's what we are trying to say. So the boron, we have that with silicon, and on like that. So this diagonal relationship present a lot of why we have what we have in them. So the next thing we want to talk about is the inert pair effect. It's an effect that everyone must know how to explain because it has a very, very important underlying factor and role is playing in the prediction of why when we are going down a particular group, you begin to see more than one oxidation state and you begin to see one more being preferred than the other. So the inert pair effect is a phenomenon that can be defined as the fact that it's an empirical observation that heavier element of groups 13 to 17 often have oxidation states that are lower by 2 units than the maximum predicted for the group. What are we saying? Immediately you are going downward the group from 13 to 17, you will experience this. Let's look at it, for example, in group 13. In group 13, the first element in the second period is boron. The next one is aluminum. The third one is gallium. The fourth one is indium, In. And the last one is thallium. You remember that this group 13 is supposed to have meant that they will have the oxidation states of +3. Why? Because they have 3 electrons in the outermost shell. So they are supposed to lose 3 electrons. So the boron will take that perfectly, aluminum take that perfectly. But as you are going more downward, something begins to happen. They'll begin to have something that is 2 units lower than what they should have been. And what do I say? What do I mean by this? That group 13 that's supposed to have +3 oxidation state, by the time you are coming down here, you begin to see another one which is 2 units short than 3, and that will be 1. You see 1 + 1 oxidation state happening as you are coming more down the group. So the thallium exhibits +1 oxidation state due to increasing ionization energy. And when the ionization energy is increasing, there is a tendency of decreasing of the bond strength. And that's why, group 13 is supposed to have been +3 oxidation state. Boron is +3, and it form compound in +3 state. If boron has to bond with halogen, it will give you BX3, where X is your halogen, because it has +3 up and the halogen has -1. They can share together. But immediately you are coming down towards the last, you begin to have, instead of +3 now, you have something that is 2 atoms short. That is +2. +1, sorry, and that will be more stable. So when you are talking about thallium chloride, you may begin to have THCl instead of THCl3. THCl will be much more stable, despite the fact that it's under the period, the group 13. So if you are coming to the group 14, which is carbon family, carbon we know supposed to have had oxidation state of +4. But immediately you are coming towards the most downward member of that group, you see +2 oxidation state coming up under that with a strong effect. So the ionization energy increases because field n-1d orbital or n-2f of suborbital are relatively poor at shielding the electron in the ns orbital. Because of, as they are going downward, their strength, bond strength is decreasing. Therefore, the tendency to shield the electron in the s orbital becomes very poor. And if they cannot shield that, then they now expose themselves to that lower state. So you can see example of the ionization energy, which is what that's dependent on for the group 13. You can see group 13, boron, aluminum, gallium, indium, thallium. And I've already told us how to do the electronic configuration in a shorthand form by just noting the electronic configuration of a previous noble gas before you arrive at where you are going. Like example, when you are looking at boron, the electronic configuration, having doing this, you must try to practice this from time to time so that you are able to write the electronic configuration. Boron, for example, has atomic number of 13. Atomic number of 5. So boron should have been 1s2, 2 electrons in the 1s orbital, 2s2, 2 electrons in the p orbital. He has 4 electrons out of 5, so we need 1 more. And we know after 2s is 2p, so 2p1. This one is easier to do because you are still close to the origin. But by the time you are coming to the period 4, period 5, period 6, your configuration will be too long. So if you look at this carefully, You remember that there's a noble gas that have atomic number of 2, and that's helium. So this 1s2 is obeying duplex rule, is the direct configuration of helium. So instead of trying to run everything full length, you can just replace this one with helium, and then this will now be the valence electron. That's why we are saying, oh, the inner electron of boron is 2, and the outer electron of boron is 2 of the S plus 1 of the P. That's why we say atomic number of boron is 5. Therefore, in this normal secondary school feeling, we can say 2 electrons in innermost shell and 3 electrons in the valence shell. But it is through this configuration you are able to appreciate this better. That these 3 electrons in the outermost shell, that you just feel as if you say, oh, the nucleus of atom of boron is here, and there are 2 electrons you feel in the first shell, there are 3 electrons you feel in the second shell. You understand and appreciate it better, to let you know that, oh, these 3 electrons that are in the same shell outside, they are not in the same orbital. 2 of them are in the S orbital, and only 1 of them is in the P orbital. But both of them are in the second shell. That's why you can see quantum number N here is 2, N here is 2. So when you look at that, you must be able to know how to do. So if you are looking at aluminum, for example, the configuration of a noble gas before aluminum is the one with atomic number of 10, 2 plus 8. An atomic number of 10 is neon. So after the atomic number of 10 is the second shell, because it's filling it. You can feel, say, neon, it will be 1s2, 2s2, 1s2, 2s2, 2p6. This has formed a total of 10 electrons, and you know neon is 10 electrons. So what you would do is that, oh, this has formed a total of 10 electrons, and I want to fill 13 electrons for aluminum. So this remaining only 3 to fill. How do I know where to fill these 3? You already know that, oh, the 10 has been filled in the first and second shell. So the electron number 11, we have to go to the third shell. Electron number 12, we have to go to the third shell. Electron number 13, we have to go to the third shell. So if I want to do a configuration for aluminum, which is 13, I can say the electronic configuration of a noble gas before him. That noble gas is neon, because you have atomic number of 10, which I could have filled like that. And when I want to get to fill the remaining 3, so this neon has filled 10. I want to fill the remaining 3. How do I know where to fill it? The 10 I feel is 2 and 8, or 1s2, 2s2, 2p6. So the electron number 11 is to go into the third shell. And you know every orbital will start with S. So you can say 3s. And the maximum electron S can take is 2. And you want to fill 3 more electrons for the aluminum. So this 3s will take 2. And next to the S orbital will be P orbital, also in the third shell. 3p. How many will you need to fill now? You have filled 10 plus 2, 12. You need 1 more. So the electronic configuration of aluminum will be that of neon, 3s2, 3p1. That of gallium is in the fourth period. You see that after you fill it with the transition metal of 21 to 30, you then continue with adding. So you must know how to fill all these things. They are very important to see the beauty of what we are talking. Now, when you look at this thallium here, you see there will be long length of configuration. There is a shielding, serious one, that will make this thallium to appreciate the 1 electron in its 6p far better to take the preceding role. Why? Because if you look at how it interacts with the halogen, which is iodine, you discover that the energy is reducing. For boron is 308.801, for aluminum 578, for gallium 579, because of a new orbital that just introduced into that place. And after that, the trend continued to go down again. And when the new orbital is introduced in the S6s, it's jack up again. And that is telling us that when we are having things of this nature, it can be predictive. Because by the time you are now reacting it and now trying to sum up the average bond energy between that metal and the halogen, you discover something unanimously happened. Something, a trend was established. You see, when that M is your metal now. If it is boron you are looking at, it will be BCA you are talking here. If it is aluminum you are looking at, it will be AlCl you are looking at here. And you remember that AlCl3 is the normal thing. So there will be 3 of that AlCl. So if you look at the average bond now, you see that of boron halide is 536, aluminum halide is 494, gallium halide is 481, and that halide we are looking at is chlorine. So you see that the ionizing energy that is in this third row, 6,828, 5,139. So it's all this one that sum up together to now give you that, oh, the average energy is reducing as we go more downward. So having talked about the generality of this, then we want to look briefly at specifically group 13 elements and group 14 elements. Group 13 element border the diagonal line in the periodic table, and the elements in that group are boron, aluminum, gallium, indium, thallium. Most group 13 elements are reductants and are less powerful than the group 1 and group 2, which are called alkali and alkaline earth metal. Their oxides are thermodynamically stable. Large amount of energy are needed for their isolation. Most abundant elements in group 13 are boron and aluminum. Preparation of group 13. You can have large scale preparation of boron as a member of the family, as the first member of the family, by reacting borax with acid. You can see the formula for borax here with 8 molecules of water of hydration. After reacting it with acid, it led to the formation of boron hydroxide, which under high thermal condition was decomposed to barium oxide. Usman, please kindly mute yourself. Usman Aliyu, please mute yourself, please. So thermal decomposition of barium oxide now leads to 2 molecules of barium, 2 atoms of barium and oxide of a beta. How did this happen? This happened by using heating up the barium oxide in magnesium. And you remember the periodic table, the electrochemical series. Magnesium can actually displace boron from the boron compound. So when you heat it up in the presence of magnesium, magnesium displaces the boron to take the oxygen to form magnesium oxide. Then why that helps boron to be stripped up of its oxygen to form the pure boron metal. The second method of preparation is thermal decomposition of diborane. BH3 is the borane, but borane normally exists in the molecular form, which is BH3 in 2 places. We call it diborane. So when you treat diborane under high thermal condition, there will be effervescence of hydrogen gas to leave boron metal. Thermal degradation of aluminum oxide. Just like with the boron, aluminum hydroxide will produce the aluminum oxide, while the metallic aluminum is obtained by electrolytic reduction of the aluminum oxide using Hall-Héroult process. Hall-Héroult process It's like an electrochemical reaction where you are able to obtain the metallic aluminum from aluminum oxide by depositing various different entity of that mixture on the cathode and the anode. When the oxygen effervescence is there to be collected, and then the aluminum metal is deposited. Reaction of the group 13 elements. Boron, as the first member of the group, because of is in the second period and a small atomic size, is able to react under high thermal condition with nitrogen gas. If you bubble nitrogen gas into the metallic boron under high thermal condition, you will form boron nitride. Boron nitride. So you must always know how to balance the chemical equation. The boron nitride, why? Because boron is B plus 3 and nitrogen is looking for 3. So you can come together to have that. Another one is the boron oxide. Boron oxide can be formed also under high thermal condition by bubbling oxygen gas. Sorry for that equation, that oxygen gas, please, let's correct it. 3 molecules of oxygen gas. 3 molecules of oxygen. You know, oxygen is a diatomic molecule. 3 molecules of it is what I meant here. It will form this boron oxide. So boron trihalide is also important that it can form because each of the halide is looking for 1, and the boron is willing to give 3. So you will need 3 of X in order for him to be able to give out all his 3. And the very simplest way of getting the molecular formula of the compound from those 2 elements is to transfer their charge to the base of each other. So when they relate together that way, B will be taking 1, X will be taking 3. So anytime you have boron being treated with group 7 halide, boron halide will be trihalide compound. So when you are treating it, for example, with chlorine, you will be using 3 molecules of chlorine gas. Why are we doing that? Because chlorine atom cannot exist in nature. Chlorine exists as a diatomic molecule. So it's you that will now know how many molecules you have to put in its front to make sure you are able to form BCl3. Boron trichloride, all of them are possible. But you should always say that the reaction of boron always proceed at high thermal condition. Boron compound with multicenter bond. Boron can also form compounds which contain multicenter bond that cannot be explained with simple bonding theory. And these are the borane family that we are talking about. They form in form of cage, not in a real line bond. If it's in a real line bond, then their atomic size and the atomic radius will not have allowed them to do that. So an example of such compound of multicenter bonds that boron forms are the borane. You can see B2H6. And you see the structure. And you can see the complex of borane here in comparison with the aluminum. Complex formation in group 13. Boron, being the first member of that group 13, will not love to form complexes simply because of its small size. It doesn't have d orbital, which is 5-fold degenerate, which has opportunity of getting excess of electron from the ligand. But immediately you are coming to the top period, which is aluminum, you're already having a low line 3d orbital, which a lone pair of electron from these ligands can be donated to him easily to form complex. And one of such ligand is water. You know, water is an sp3 hybridized compound with 2 lone pair of electrons. So you could donate lone pair of electron into empty d orbital of aluminum in order to form compound with aluminum. Boron is poor in complex formation. However, aluminum, gallium, indium, and to a low extent, thallium can form complex. Why is thallium to a low extent not like good extent like aluminum? Despite the fact that it's an heavier member. Because by the time you are coming to thallium, inert pair effect is already taking place. And therefore, instead of it to be more stable at +3 oxidation state, it's more stable at +1 oxidation state. So you will have a low affinity to get more of those ligand to him, but you can still form it better than what boron will do. So the simplest member they form is M with 6 molecules of water of hydration. And why is he having overall charge of +3? Because water in the rules of ligand formation, it doesn't have the charge. And therefore, when you are saying that of water is 0 and your metal is in group 13, which has oxidation state of +3. So the overall oxidation state of aluminum hexahydrate will now be 0 + 3. And that's why the overall charge is +3. So the simplest are M with 6 water of hydration, which are relatively strong bronstelluric acid, electron pair acceptor, and can lose a proton to form this compound. A complex that's disproportionate into 5 molecules of the water and the hydroxyl anion. Why is this still having overall oxidation state of -3? Because the water is 0 in that place. So this is an equation of that. So complex stability increases as number of coordinating group increases. So the more the number of the coordinating group that want to donate to the empty center of this stable group 13 element, the better the complex that will be formed. And that's what formed here when the ligand there is oxalate anion. Aluminum is willing to form a center with 3 molecules of that oxalate, and it's much more stable. That's why we are saying the complex stability increases as the number of coordination group increases. Group 14. The group 14 are having some very unique property, especially the first member of that group. They displays greater range of chemical behavior than any other family. That's why carbon, has been the first member of this group, is the origin of organic chemistry. The chemistry of carbon and hydrogen is a unique word of the soul that because of the excellency of carbon. Carbon has atomic number of 6 with 2 electrons in the inner shell and 4 electrons in the outermost shell. And it's 1s2, 2s2, 2p2. When you promote the 2s2 electron, you have half-filled orbital, which confine high stability on carbon. And it's also have a very balanced hybridization system that makes it to now catenate to be able to form carbon-carbon bond that can run to thousands, that can run to millions, which is the origin of our molecule. So when we look at that, you see that the carbon is having 1s2, 2s2, and 2p2. And the one of the higher energy are the one in the second shell, and they are the valence electrons, sorry, 2p2. When you are promoting that from the ground state to the excited state, you discover that your 2s will have, and your 2p will have. Electron enters singly first before pairing. If you do it at ground state, you see the 2 electrons of 2s will be like this, 2 electrons of 2p will be like this. But at the excited state, before you now blend the s and the p orbital, what happens is that the electron is promoted from inside of that s, and then it will jump and form on that p. And you see that they are half-filled electron. An half-filled electron is as stable as a fully filled electron. Can somebody tell us? List the first five members of group 14. Yes.
Carbon.
Very good.
Silicon.
Carbon number 1. Silicon number 2.
Silicon.
Yes.
Germanium.
Germanium. Very good.
Tin.
Tin.
And lead.
You see, tin is SN. You wonder why is tin SN? They use the Latin name of tin so that it will not confuse with other elements that have T. So tin in Latin name is Spanion. Spanion is SN. Then what's the last one?
Lead.
Lead. Very good. Plumb bomb. Lead. So this is it. There is no big deal if you can get that. There is no way you cannot be able to talk about their chemistry. And if we are talking about group 3, can we say it? Can somebody help us with the first 5 members of group 3? Or group 13, sorry. Group 3 was the whole group numbering. Group 13 is what we are using now because of that 10 transition method that we have to add. So group 13, the first member is what?
Boron, aluminum,
very good.
Gallium, indium, and titanium.
And thallium. Thallium, very good. Okay, based on the position of group 14 elements in periodic table and the general trend outlined in this section, can we classify this element as metal, semi-metal, or non-metal? A metal is something that is towards the more electropositive, willing to donate electron. The non-metal are closer to the electronegative side, willing to accept electron. And the semi-metal are in the borderline, that they may want to behave like metal to donate, and they may want to behave like a non-metal to accept. Okay, all these ones are already what we have dealt with, and you can check them up in your notes. If you have any question on it, we can talk about that next week. Predict which element form the most stable compound in +2 oxidation state. Among all these group 14, which one of them will be able to form a more stable group of +2? You remember that group 14 normally should have been +4 oxidation state. But we are saying as you go downward towards the last member in the group, there will be inert pair effect that will make him to be more stable at 2 value short of the normal oxidation state of his class. So the normal oxidation state of the group 14 class will have been 4 because 284 or 2884. But what we are trying to say, 24, sorry, or 284. But what we are trying to say now is that which one of these elements will be more stable at +2 instead of +4? Because of that inert pair effect. You are going downward, lead will be stable in +2. That's why when we are talking about, carbon chloride, carbon we use is for oxidation state full, the carbon chloride. The most stable chloride of carbon will be carbon that have that 4. But the most stable chloride of lead will be the one that is using oxidation state of +2, which is PbCl2. This is why. So if we are saying, normally group 14 should have a tetrahalide as their compound with halogen. Can you explain why lead is preferred to be PbCl2 instead of PbCl4? That inert pair effect make this one to have a high level of shielding, and therefore we prefer to be going to form products with the non-metal in its +2 oxidation state, despite the fact that it's not in group 2. So what is the product of hydrogenation of but2 ion in boron? If you look at the family of boron, we said its hydrogen is negatively charged because boron will be more electropositive than hydrogen. So when you say BH3 or B2H6, those hydrogens are negative hydrogen. And you remember when we talk about the uniqueness and the specialty of the hydrogen. Hydrogen has one electron. It doesn't want to transfer that one, but at the same time, you can collaborate by covalently bonded with something to share that one as +1. That's when it becomes a proton. Or you can borrow one to become a negative -1H. That's where it's an hydride. So boron is an hydride of boron. And when you are hydrogenating a triple bond with it, it will form a cis-alkene. It will form a cis-alkene. That's one of the uniqueness of the boron in reaction with unsaturation. When you look at butyne means you have carbon-carbon triple bond on position 2, and position 1 is a methyl group, and the position 4 is a methyl group. If you treat this with boron, you know, addition of a molecule of hydrogen comes to turn this one from a triple bond to a double bond. But when you come to double bond, then it becomes stereo specifically inclined products. Because at the double bond, by the addition of those two hydrogen through the reaction with boron, we now have tendency to form a coplanar molecule. But if it is boron that you are using, we are saying that your two bulky group on the two carbon-carbon double bond will be on the same side of the plane all the time. So boron is a means of producing this kind of compound. And when the two bulky group are on the same side of the plane, you have what is called cis isomer of alkene. So boron is useful in selectively producing a cis alkene from an alkyne. And this compound now, because of that, is named with the cis butch 2-ene. C butch 2-ene. Because when you add a molecule of hydrogen to ine, it becomes ene. So that's all we're saying there. What are interstitial carbide? You remember that carbon is a first member of group 14. And anytime is coming as a negative charge, is called the carbide. If you have calcium as a positive that you are thermally heating it up in carbon, it will form calcium carbide. Silicon carbide when you force it under thermal condition with silicon. So anytime carbon is adding to a metal as a negative, it is called carbide. Anytime hydrogen is added to a metal as negative, it's called hydride. So the reaction of carbon with most transition metal at high temperature produces what is called interstitial carbide. You remember that metallic carbide is formed when carbon is the negative that reacted with other main group metal. But if the carbon is reacting at high thermal condition, not with the main group metal, but with transition metal, that's where you form interstitial carbide. Due to the less electropositive nature of the transition metal, this carbide contains covalent metal-carbon interaction, which result in different properties. Most interstitial carbide are good conductor of electricity. They have high melting point and are among the hardest substance known. Interstitial carbide exhibit a variety of nominal composition, and they are often non-stoichiometric compounds whose carbon content can vary over a wide range. Among the most important are the tungsten carbide. When you use tungsten metal and heat carbon up in tungsten metal under high thermal condition, it forms tungsten carbide. Remember, tungsten is transition series, iron is transition series, and that tungsten carbide is used industrially in high-speed cutting tools. Another one is called cementite. A cementite is iron carbide. When you treat carbon under high thermal condition with transition metal called iron, you form cementite. And it's used majorly and is a major component of steel in the iron and steel industry. Reaction of carbon and its compound. A compound of carbon here is treated, HCO2H is formic acid. When you treat formic acid in aqueous sulfuric acid, it's going to give us carbon monoxide gas and then the combination of Lewis acid and Lewis base, as you can see in that equation. And further treatment of the carbon monoxide with chlorine, we form what is called phosgene. Phosgene is C-double bond O. We took chlorine linking to that carbon to fulfill the tetravalent nature of the carbon. This phosgene has some peculiar nature, despite the fact that it's very toxic. Phosgene is an important industrial chemical that is prepared on a large scale, primarily in the manufacture of polyurethane. And of course, you know, polyurethane is a polymeric compound that is the main stock in your foam that you use to sleep on the bed at home. So this is another reaction of the group 4, which is the carbon, is reaction of carbon with sulfur. It gives us carbon disulfide. Carbon disulfide. Remember, the first member of that group of sulfur is oxygen. When you react carbon with oxygen gas, it will give you carbon dioxide. So the next member under the oxygen is sulfur. If you react it with sulfur, it will give you carbon disulfide. Before we go and summarize what we have done today, I'd like to ask if there's any question. No question. Thank you. If there's no question, by God's grace, in conclusion today, we have been able to, number one, know and classify the elements in group 13 and 14. So by now, every one of us can number all the elements in group 13 and write their electronic configuration. We can do that for group 14 too. We understand also the electronic configuration of those groups. We have known the concept of the ion pair effect that make the most downward member of this group to exhibit a more stable oxidation state, which is 2 value less than the normal value. Like group 14 should have had oxidation state of +4. But when you are going downward towards the last member, like the tin and like the lead we prefer to be more stable at +2 oxidation state. While tin we exhibit both +2 and +4. While carbon as a first member, we exhibit only +4. So this last member of the group, as you go downward, having an oxidation state that is 2 value lower than the normal is as a result of the inert pair effect. We have been able also to know the reaction involving in group 13 and 14, and also the application of such compound or of such element or their compound in everyday today activity. It's on this note we have come to the end of the class for today. Good night and stay blessed.